Now, what happens in a base-promoted halogenation of aldehydes and ketones? So in this one, you don't get a mono substitution. You actually get multiple substitution, polysubstitution. What do we mean by that? So it says here, in the base promoted reaction, all enolizable H's, and here they are, should always be able to point them out on the alpha carbons. You have two alpha carbons here. All of these alpha hydrogens are substituted with halogens. So what happens is the following: Br, 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 and Br. So you had the polysubstitution here. All of the alpha hydrogens were converted to bromines. However, if you use a methyl ketone, you actually get a totally different reaction. So a methyl ketone, meaning you have a methyl as one of the R groups attached. So in this case, you have an R group. Let's say it's an ethyl, and then you have a methyl. Here's your methyl. If you have a methyl ketone, you actually get an unstable intermediate, which is CBr3. You had all the substitution take place here. So this is unstable. And if this undergoes a few steps, first adding a base, then an acid, you actually end up with a carboxylic acid and something called a bromoform. Okay, you heard of chloroform? So this is now the bromine version of chloroform, where you have 3 bromines attached to a carbon. And of course, there's a hydrogen on that carbon. So it's like chloroform. Now, you also can have an iodoform. So if you actually use iodine, you actually end up with, after the reaction takes place, et cetera, also end up with the same carboxylic acid plus HCI3, which is iodoform. Now, what is the mechanism for this? Now, I'm going to, and I say that here, by the way, with the iodoform, so it's already mentioned. But what is the mechanism, really quick here? I'm going to take a shortcut when we do the mechanism, simply because we have other mechanisms to worry about. So the mechanism involves the enolate, and that's the key part here. The enolate is the key part. So again, it's a big mistake if you use the enol in the basic conditions. Remember, the enolate is what you use for basic conditions. Let me just redraw this. Okay, so you form the enolate here. Once again, this could be the double bond here as well. That works as well. Remember, this is the better form. Again, you could have done it all in one step, but But the negative, putting the negative on oxygen, remember, makes it more stable because it's more electronegative. So here's a bromine. Electrons come down, kick that out. Now, of course, this reaction, after you add the bromine, let's just fix this a little bit here. It repeats twice. You deprotonate the H, and then you form the enolate, attacks another bromine molecule, so on and so forth. So repeat twice, and you actually end up with, finally, polysubstitution here. So you have CBr3. Now, when you get to this point, the OH is going to attack the carbonyl. And the electrons, remember, are going to come down. And this is kicked out. It's a better leaving group because you have 3 bromine atoms attached. They actually have the inductive effect. And then you end up with this, which, by the way, can be in the carboxylate ion form as well. And then, of course, it gets protonated. So that's the alpha halogenation for base promoted and acid catalyzed.